I'm pleased to have with us today Dr. Iain Marshall from the Faculty of Life Sciences and Medicine at King's College London, and he'll be talking to us about new models for evidence synthesis using machine learning / artificial intelligence. So off to you, Iain.
Hi, I hope you can hear me all right, and my slides are showing. Thanks for inviting me along to give a talk. My name's Iain Marshall. I work as a senior lecturer at King's College London. My background is I work as a GP or a family physician, and still do a day a week, and then spend the rest of the week doing medical research. And a large proportion of the time doing research into methods for research synthesis. So today I'm going to talk about let's see if the slide not try that. Excuse me while I try and advance the slide. So today I'm going to talk a bit about some of the work that myself and a large number of collaborators have been involved in, and looking at areas where machine learning and natural language processing can be used in evidence synthesis, and also some of the areas where it can't be used in evidence synthesis. So hopefully we'll cover some of the basic principles of what these methods are doing, and so you get an idea of when they might be able to be used. We look at which process of the systematic review you can automate, and then also to look at really how some of these methods might enable us to move beyond conventional systematic reviews and look at new methods of evidence synthesis in the future. The last thing I'm going to have a chat about is a new project we're being involved in called Robot Reviewer Live, and I hope to show you a bit about how it works and invite anyone interested to take part in a pilot. I have an enormous amount of acknowledgements, but it's to reflect that most of the work I'm going to present today is not just mine, and very much involves a lot of these other people and many others. So Byron Wallace, Tom Tricolinas, Joel Cooper, James Thomas, Ben Nye, Anna Olstor, Rachel Marshall, Frank Sobichevsky, Anna Nenkova, Gregory Kell, Hyson Young, Mark and Stevenson, to say a small number. And also with some recent thanks to Northeastern University AI Centre, who are hosting some of our projects now. So, first of all, this is the typical situation of anyone conducting an evidence synthesis, and that's piles and piles of paper. And so the incentive to try and automate some of the drudgery or some of the laborious work of an evidence synthesis is quite obvious and strong for anyone who's conducting one of these things. A typical systematic review might take up to 2 years to do. That's not unusual. Some may be longer. It's possible to do, there's papers out on doing 1 in 2 weeks, but it's quite hard work, no matter which way you do it. And so any ways of improving the efficiency of how these reviews work is the big motivation for a lot of what's going on here. And so the first thing really to talk about is when people talk about machine learning or natural language processing, what is meant? And for the most part, we're talking about algorithms which are very much like statistical models. In fact, they are statistical models, and they work very much the same way as a logistic regression model might be used to go and find out if a risk factor causes an illness. And in fact, logistic regression models to work out if texts are related to some outcome or other are one very effective means of doing this. And there are more complicated models than that. There are logistic regression models, and you've got things which have moved slightly up in sophistication to one called support vector machines, which are illustrated here, to the state of the art at the moment, which are neural network models. But they all essentially conceptually work in the same way. The type of learning is called supervised machine learning, where you start off with, if there's a task you want to complete, you do it on a large chunk of documents manually. the process called training. So if you had a classification task, if you had a huge pile of documents, which we do when we're screening abstracts, and we want to separate them into the relevant abstracts and the irrelevant abstracts, what one can do is take some large number of documents that someone as human has manually gone through and labeled as relevant or irrelevant, and train one of these algorithms. And then later on, when you get an unseen document, you can go and automatically assign a label. So that's the last task is a classification task. You're getting a document and you're trying to assign one or more labels to it. Another common method is information extraction, and similar algorithms are used for this. And it's the same idea at play, that let's say you wanted to go and find some text inside a document, which was, say some text span, a sentence or a sub-sentence, which describes some piece of information you wanted in a systematic review here. If you want to know about the PICO or text describing the risks of bias, you would get a large number of such documents and manually label them. And stick them through one of these algorithms, and in the hope that they would be able to repeat the task of finding these types of texts automatically. And both of these methods work in practice reasonably well, as we'll come to later on. Generally not quite as well as humans, but reasonably well. And so one of the big tricks, or one of the big things that we have to do in looking at automation, is trying to figure out what types of tasks are amenable to automation with suitable quality, and how do you get human scientists in the loop to try and validate and make sure that the pieces of information are correct. So conceptually, a lot of automation work is based on classification and information extraction. So we were saying documents are relevant or not, or we're trying to extract information from documents. And you could consider a large chunk of systematic review conduct is translating what they call unstructured information, so human English text, as you see in the PDF on the left, into a structured format, as we see on the right, where we have either spans of text or even structured vocabulary elements, where we standardize terms for different medical conditions or study designs or so on. So I think one of the interesting questions is about the limits of what AI and machine learning can do. And I've seen a lot of perhaps overhype, or people describing things which are fundamentally going to be impossible with this current generation of artificial intelligence. And this is just a quote from Bo and Jeka's Kamanovich. Engagement with the literature is not a routine task, but an intellectual development process. And they're describing how in conducting a systematic review, there's actually a huge, despite the fact that actually most of research synthesis methods and methodology development over the past 25 years is all about increasing the rigor, increasing the transparency, and increasing the reproducibility and the objectivity of research. There's an awful lot of systematic reviewing which is subjective, and rightly so. And I think it's probably a much higher degree of subjective expert judgment than many people appreciate. One of the obvious examples is when you're designing a systematic review, and just things as simple as thinking, what is the research question? What should be the inclusion and exclusion criteria? How should we treat certain elements? And Bo describes how even just deciding whether an abstract meets a rigorous predefined inclusion criteria is in itself a subjective judgment, and there's often a lot of translation of the language trying to infer what authors of trials have actually done, and it's often a lot more subjective. And in that light, it's kind of intrinsically really difficult to use automation or machine learning or artificial intelligence at all. And just a couple of examples. these are three different systematic review summaries, A, B, and C, all looking at the same question, which is about the use of statins in primary prevention. So trying to reduce cholesterol in people who've never experienced heart disease or stroke before in order to prevent death. And three systematic reviews done all within a couple of years of each other, about 10 years ago, all came up with kind of different answers. And the reason they came up with different answers is they had different attitudes to the inclusion criteria. Systematic review A was done by the Cholesterol Trialists Collaboration, and they included any sort of study which happened to have, many of the studies happened to have people who had some form of angina before. You know, that happens a lot where trials are not quite as pure in the population as your research question is. And then research group B, they will allow, they said if there was more than 20% of a population who had a pre-existing angina, they would exclude the trial. And they found a slightly broader result. And then C, when the reviewers who decided that they would only include studies where no one had had pre-existing angina, they found a much broader and non-significant result. And none of these are essentially right or wrong, but it just shows the importance of subjective scientific judgment in the design and implementation of systematic review, and how automation, where it exists, is not likely to bring you for another generation to anything approaching a systematic review from scratch. This was another example of this I found quite interesting recently. And I find it interesting just because of having spent a lot of time trying to automatically translate texts into essentially 2x2 tables to go and find out who's had what. And this is the one of the preliminary studies that came out about the AstraZeneca COVID vaccine study. As you may know, this trial was done across multiple countries. And one of the things which happened was that inadvertently, a large number of participants received the wrong dose. So a chunk of the people who were enrolled in this trial received, I think it was half the dose of the vaccine. And then it turned out that the people who received half the dose of the initial vaccine had, it turned out, higher vaccine efficacy in this study, which seemed odd. So ultimately, at the time of trying to think of automatically generating 2x2 tables to go and inform a meta-analysis, it's never going to be possible to have any sort of standardized, predefined, utterly automated process of translating text into one of these tables, because this kind of thing, I think, happens all the time. And somebody needs to have a good old think about it. And how do we treat this sort of data? What's important? And two people might not come up with the same way, but a lot of the research synthesis process is or does involve a lot of subjective scientific judgment. So that's important background. And so with that in mind, what's the point, or is it possible to do any automation? And I think it is, but I think we need to take a lot of care about the type of tasks that we use automation for, have some careful consideration about how well it works, and also to consider about how do we ensure that any automated results are valid and checked by humans in an appropriate place. Here's three of the most common areas where automation is used at the moment, and that's around search, abstract screening, and data extraction. And on the whole, the classification models I've described have been used quite widely for selecting studies from research databases. Oftentimes, these models will work well enough to safely remove the vast majority, but not all, of the irrelevant articles. And a model where you get a human to go and look at the remaining, to go and filter out the final ones which are relevant, has been used quite widely now, and does seem to work quite well. So you can fully automate the bit of excluding a large chunk, but not the full chunk of everything. And then going on to data extraction. And again, we can use these data extraction models to go and identify pieces of useful text in articles which are relevant to any particular extraction task. But with the state of both because of the state of the accuracy of such models, and conceptually because ultimately we're dealing with a sort of intellectual, subjective, analytic task for which needs some expert input. It's for the next generation of AI systems. You would like a human researcher to go and check what's going on at minimum. Here's just a illustration diagram of how you might consider the effectiveness of automation systems. I think the first thing to highlight is that current practices, there's not always a very solid research evidence base to go and justify why things are done as they are. There's often a theoretical basis, but there's not often rigorous evidence to go and support things. And so, for example, if you want to know how accurate two humans doing a data extraction is, and whether they should be blinded from one another, and oftentimes these methods make sense, but they're not necessarily, the accuracy of these is not necessarily known. So it can be sometimes difficult to determine what's a gold standard. But in principle, you could imagine there's a theoretical gold standard where the data is all correct, and double human extraction is conventionally done, and is some very high number of accuracy, but somewhere below 100. And then a single human might be below that. And we could imagine that a system which performs as well as two humans, as the current status quo, you could fully automate a task in that way. If you had a system which was as good as one human, perhaps you could replace one of the two humans and make some significant gains. And then lastly, if you've got some system which is less accurate than even one human alone, it could be potentially useful for assisting humans. So, removing clearly irrelevant abstracts in a classification system, or highlighting areas in the text which might be useful for evidence synthesis. It so happens that the overwhelming majority of AI systems and NLP systems are probably in that last category, below the performance of a single human. So we have the challenge of can we make them the most useful for conducting reviews? This is now just to introduce our system robot reviewer, which we've called the same name for a number of years, but has evolved in what it does. But essentially, robot reviewer is a machine learning system for data extracting information from clinical trial articles. And it works over both abstracts and full text articles. And it started off from a chance meeting in a Cochrane Tech conference in 2013, where I met Byron Wallace, who's my main collaborator, and we've been playing around with some data in Cochrane reviews, and we noticed that there were a huge amount of structured information on risk of bias assessment in Cochrane reviews. And so we figured out a way of linking up the PDFs from the full text of these papers with the judgments in Cochrane reviews. And we managed to generate 12,000 abstracts, sorry, 12,000 full text articles as PDFs, which had risk of bias labels, which had the labels both for the judgment and also the supporting text, the rationale for the judgment. We created a system where we had a collection of models which were able for an unseen article to go and determine whether a new trial is likely to be at low risk of bias or not. And so the system works where if you send in a new article, it will go and extract the text. It will identify spans of text which are relevant to 4 of the domains of the version 1 of the Cochrane risk of bias tool: random sequence generation, allocation concealment, and blinding of participants and personnel, and blinding of outcome assessment. And it will give a suggestion about the risk of bias judgment as well. When we looked at the accuracy of the system, we found it was inferior to human assessment, but not too badly inferior. It was about 7 percentage points inferior in terms of accuracy. But we found in practice, and that was followed up by a randomized trial we did, and with some qualitative component, and we found that people were finding that the supporting text was quite useful, in particular for low risk of bias decisions. So people were finding it generally quite helpful as a sort of a recommender system to try and help them using the website to go and make these judgments. And so we have made Robot Reviewer available on this URL, demo.ieai.robotreviewer.net, and you can try it out and upload some PDFs and see how it works. As well as we've used Robot Reviewer as our collection of models over the years, and we've sort of gradually expanded it from just risk of bias to extracting information about PICOs from the full text and from abstracts, doing study design classification. We can now classify lots of different study designs as well as RCTs and also assessing risk of bias from abstracts, or indicative risk of bias from abstracts, which we'll come to shortly. The classification model we developed in Robot Reviewer for identifying RCTs from search results has been quite successful. And we did a study to go and figure out how well it worked compared to conventional search filters. And it turns out that machine learning models do work better than search filters, and you can match the sensitivity of the Cochrane highly sensitive search strategy. So you find exactly the same number of trials, but with a significant jump in specificity. So we go from 76.9% specificity to 87.6% specificity. And it so happens that makes actually quite a dramatic difference to search retrievals and results for further screening, because we're dealing with a minority class. The precision of the positive predictive value jumps quite a lot. And so it turns out, if you, on average, the Cochrane highly sensitive search strategy might get the retrieval of those, only about 6 to 7% of those retrieval will actually be RCTs, and the rest will be manually filtered out. Whereas you go to machine learning, it goes to about 21%. So you get a dramatic, or well, I don't know about dramatic, but you get a substantial reduction in workload if you use a machine learning RCT filter. Sorry, my pointer's disappeared. I just wanted to put this quote because it's a nice introduction to the next task. It's a surely great criticism of our profession that we have not organized a critical summary by specialty or subspecialty adapted periodically of all relevant randomized control trials, which is of course one of the quotes inspired in the Cochrane collaboration. But one of the projects we worked on next is called Trial Streamer. So we thought, well, what would happen if we could sort of apply some of these machine learning models at scale? And I think this is quite broadly a really interesting application. Whereas in thinking about sort of new models for evidence synthesis, we're often fixated on doing the same as what we're doing at the moment, but sort of automating things, and we're sort of coming up at the barrier that AI is not as good as human application. But it also has some strengths, and one of them is you can analyze vast quantities of data, which would never be possible. And so this project's really around that, is like, can we get these decent but slightly imperfect models and apply them at scale to make a useful system? And so this is the search engine that is available at the URL at the top. But just to describe what we're doing here, and in TrialStreamer, we've aimed to classify and extract information from all the articles in PubMed. And also, we do the same from clinical trial registries. So we use ICTRP to collect clinical trial registry data. And we get these sources of information to try and find RCTs. And we start off by using our machine learning model to identify studies which are RCTs. And we keep those and discard all the rest. We then go and find out, is the trial done in humans? We have a separate model which does this and keeps anything which is and discards the rest. So we should be left with a collection of human RCTs. Everything which is left, we then go and classify and extract information from these articles automatically. And so specifically we get information about PICOs, and we extract structured vocabulary information. So mesh terms or related things about the population interventions and outcomes. The number of people randomized. We can also extract the text of the author conclusions, and we've got a model which sort of gives an indicative idea of the direction of the effect of the study. So we go through that system, and the results, all the structured information, we pop into the TrialStreamer database. These are the recall and precision statistics for all the components of the model, and just a couple of things to describe about how well these things work or don't work. The first of all is what we're keeping as RCTs. One of the nice things about machine learning models is if you compare it to a search filter, which is fixed and it's quite hard to adapt, machine learning models, actually, their thresholds for what you say is includable or excludable are infinitely tweakable. So you can go and say, right, well, I'll take a little bit less recall and improve the precision. And that's what we did here. And I described if we have 98.5% recall, we ended up with 20% precision before. So 80% of the articles weren't relevant. Whereas here, we adjusted the recall a bit and we got a dramatic improvement in precision. So we find 97% of the trials, but the vast majority, well, not the vast majority, sorry, a majority of the documents in TrialStreamer are genuine trials. Other things to point out is that we have got some, in terms of the PICO concepts, we've got pretty good numbers for the recall. So we're identifying all the right contents for the PICO concepts, but precision is lower. So we are identifying some irrelevant concepts as well. And that was important for how we designed the system, because a lot of the irrelevant concepts, it turns out, were very irrelevant and not likely to be searched for. So in fact, that when you search for any clinical terms, it's not the case that the wrong articles will come out for these clinical terms. So searching for these work well. And then the last thing is that the way we treat risk of bias, because we're only using the abstracts. And so we trained a model to go and predict whether articles were likely to have a low risk of bias in multiple domains of the tool, but using the abstract only. And as you might expect, because that information is often not there, the recall and precision are less good at 0.46, 0.44. But that's fine. And so the way we treat that is that although the actual discrimination wasn't great, you wouldn't want to use that as your final way of assessing which articles are of good quality or not. The calibration wasn't too bad at all. And so we were getting very good error under the ROC curve, and the calibrations were looking very reasonable. And so it turns out in practice, when we're using this type of model, because there are features in an abstract which tend to be associated with better quality. You know, you could imagine that abstracts might report well, whether a study was blinded or used a placebo control. That's just one example. Or how prominently the word randomized is used, perhaps, I don't know. But these things might not be definitive, but they're associated. And so we use this not to go and say whether the trial is good quality or not, but we use this as part of a ranking system, so that when you go onto the trial streamer page, which I'll show you in a minute, you can go and identify or pull up to the top of the screen the studies which are likely to be at the lowest risk of bias. And I think it's just another example where you can get a model which for some purposes wouldn't work well, but for other purposes can work quite acceptably. So this is the first result from Trial Streamer. And the yellow line is if you were to go into PubMed and search for the publication type randomized control trial, you'd get a line which looked very much like the yellow line. And it sort of has worked all right over the years, but unfortunately, it just happens that a lot of the publication type tag is manually applied, or certainly has been. And so in practice, what we found was in the last 5 years, there were around about 50,000 RCTs, which we were able to identify from PubMed in the system automatically, which were or had not been identified by yet by the manual tagging. It's likely to change over time, especially as PubMed moves to some automation itself. But by using these automated systems that we can, these are run essentially automatically, and they're run daily as soon as the PubMed update is published. So we're able to essentially live capture any new publications of trials. And here's what it looks like if you were to go into the website and search in this example about how effective anticholinesterases are in vascular dementia. We have sort of extracted information. These are the text spans which describe the population. We automatically have determined that there's 1,219 people in this trial. We have the author's punchline, we call it, but that's there for a summary. Interventions and outcomes. And so these are all automatically extracted. And this is the raw text from the study, but we also translate those wherever possible into structured PICO labels. And one thing I just wanted to highlight here is because we extract information about risk of bias, this is how we use it. So if you click onto the get large high quality trials first, we order it so that if you had a large retrieval, the biggest trials, which are likely to be at the lowest risk of bias, would come top on the list. And so the next thing we did was to look at some of this data, really to sort of do some bibliometric research and try and understand about what trials are being done at scale in a way which wouldn't have been possible to do manually. And so this is the first figure. We just a simple plot of how many people are in trials. You can see that in our collection of trials, which was about 600,000 trials, that most trials still kind of small. It gets unusual to have 1,000 or more, and it is interesting given that there have been many people calling for fewer large trials. We're still having huge numbers of very small trials being done. We use some of the data to go and have a look at where trials are being done worldwide. So we've got a heat map here where the darker red colors are where more trials have been done. And it's clear how, in terms of global health research, that the overwhelming majority of clinical trials are still being done in a few countries: US, Canada, UK, Europe, increasing numbers in China and India. But if we look at Africa, there are comparatively few trials being done overall. And what we did is we linked some of this data to some data collected by the Global Burden of Disease Study to try and identify, could we find out whether trials are being done where the need is, where there are most problems with disability and death from studies. And this is one of the key things we found out. So on the left-hand side, we've got the 18 or so categories of health problem as categorized by the Global Burden of Disease study. And the bars represent the number of DALYs, disability adjusted life years, so death and disability caused worldwide by each of these groups. And as you might expect, the biggest causes of death and disability worldwide are cardiovascular diseases, maternal and neonatal disorders, and respiratory infections, and TB and neoplasms, cancers. And then on the right-hand side, we attached the data we found about where our trials being done. And because we were able to extract information on the PICO, we could find out where the trials were recruiting people with these conditions, or looking at trying to look at these conditions as the outcome. And there are some marked discrepancies. And just to look at some of the obvious ones, the amount of research which is done on mental disorders and other non-communicable diseases. So those are things like obesity, diabetes, and a lot of other things. But if you compare to some of these very low research areas, so enteric infections, there's very, very few trials done looking at that. Respiratory infections and TB account for a huge proportion of the global disease burden, and very few trials are being done. And so this is just another example of how you could use automation to do very, very large scale analysis, which wouldn't be possible to do otherwise. This is what we found out about trends over time in studies, and this is the studies done in these particular populations. Yeah, there's some really interesting trends you can look at. You can see that the clinical trials looking at mental disorders have skyrocketed over the last 20 years to be the leading clinical trials area, whereas we still have very low numbers of trials for respiratory infections and TB. It's not really going up very much despite the large burden. We put it all together into a scatter plot, and you can sort of the line of best fit going through the middle, but you can see the kind of conditions which tend to have high levels of research for the global burden above the line, and ones which tend to have low levels of research below the line. And again, you can see that self-harm, interpersonal violence, enteric infections, neglected tropical diseases and malaria, respiratory infections and TB, essentially many of the problems which are predominantly affecting low middle income countries and the places where the trials are not being done. And whereas the places where the trials are being done, the global clinical trial attention is focused on these other conditions. And for anyone who's interested, we've released pretty much everything we've done as open source software to both encourage people to try and install it and use it, and to encourage people to contribute to these projects. And most of them are between mine and Byron's GitHub page. But here are some of the key ones. Robot Reviewer, Trial Streamer, and our new version of Robot Reviewer is RRNLP, where we've got our latest collection of machine learning models in there. So lastly, I want to talk a little bit about our most recent work, or what we were currently looking at, which is a project called Robot Reviewer Live. And so this is a project we have come up with, and we're sort of in the stages of piloting it to find out whether it or if it works well or at all, and how useful it can be. And so Robot Reviewer Live, what we're aiming to do is to see if we can use machine learning to facilitate live systematic review updates, or at least contribute to them, and so forth, with awareness of how well these things don't work, and getting things in the right place and getting some humans in the right place. But this is how it works roughly. We are currently looking to examine whether we can look at systematic reviews of RCTs, because we're going to use a trial streamer database, which is daily updated. In this particular example, which we have tried out already, we did a pilot already with a systematic review of COVID-19 vaccine research, which I'll tell you a bit about the results of in a moment. But roughly what happens is we monitor trial streamer daily for all new trials. We have a system which identifies any research where the PICO is right for a particular review. And in this case, we find studies which look at COVID-19 vaccinations. We then get these studies and we feed them all to a machine learning model, which is based on a technology called BERT, which is a neural network model, which happens to be the state of the art for text classification. And this model is trained on the primary searches from this review. So this is a sort of situation where you have an existing systematic review, which you might want to update or keep live up to date, convert a conventional systematic review to a living one. And so we have a model trained on the manual search decisions from the study inclusion and exclusion from that review. And then we apply it automatically to these new studies, which are published as they're published daily. Then as soon as there's any potentially new relevant research, we send an email to the system sends an email automatically, say there's some new research you might want to have a look at to the authors, and they go and sit down and have a look at step 4 and say, is this interesting or is it not? And then instantly, essentially, when the author determines what's includable or excludable, we are able to publish a fully automatic update. And we make this available at the moment as a section on the website, but we've also have technologically, we have an API. So we're hoping, or one thing we would love to investigate is whether we can incorporate this into actual publications. Could we have a section of an abstract which would give an indicative idea of new research which is waiting to be included in systematic reviews? And so in this example, this is a genuine example. We ran this pilot with Tom Tricolinos and the research synthesis team at Brown, and they went through the system on this COVID vaccination review, and we were able to automatically generate this text. Since the review was published, TrialStreamer has identified 41 new studies which appeared eligible to include. The review also reviewed these studies manually, and 19 were judged relevant, waiting to be included. So we're able to come up with some useful information. I think that'd be really useful. I hope it will be very useful for people who are reading a systematic review, which might be done a couple of years ago, and you have an idea about what's likely to be the currency of that review. We made a user interface which is reasonably straightforward to use, and if you want to go and register your review, you just type in the name of the review. You need to upload a spreadsheet with your article decisions from your initial search, and you put in the last date of your manual search, because that's when the system will start surveilling TrialStreamer from, and then you add some tags, and then an hour or two later, you will have the system will have trained a model, and we'll start surveilling TrialStreamer. And then you have a dashboard. So the user would see, they could potentially have several reviews, and it would tell you how many abstracts are left to screen. And when you go into one of your reviews, you'd see if you have any new abstracts to screen, and you can include or exclude them there. And so every time you click include or exclude, the automatic update is automatically published. I keep this here for completeness, but this is very much a work in development. But the more state-of-the-art and less reliable side is we're exploring the use of neural network models for generating narrative summaries of new research. The short summary is that they are excellent at generating plausible English text, but less good at generating scientifically reliable text. And so one of the areas we're investigating at the moment is how does one even assess or count, because there aren't any very good metrics actually for looking about whether a text is scientifically correct or not. So we're trying to look at, can we develop some new metrics for figuring out how correct a narrative is, and also trying to look at, is it possible to generate machine learning models which will produce narratives which are more faithful to the scientific results. this is just to give an idea of what happened in our pilot with the COVID vaccination review. So in this one review, the reviewers included 38 studies and some searches done in February last year. And so we took their February searches with their inclusion and exclusion decisions and put them in Robot Reviewer, which trained a model. And that ran for about 6 months from February through to August. And during that time, Robot Reviewer identified 79 new studies. And it so happens that some of them, in fact, most of them were identified before the authors did the update searches. And some of them were identified between the time when the authors did the update searches and I had screened them. So we were able to sort of keep slightly ahead of the game there. And that compares to 135, which came from the update searches. And so the manual process, which was run in parallel, they ran a manual process from February through to August, and they came up with 31 eligible abstracts. After manually screening 135 found through searches, and using Robot Reviewer Live in this example, we identified 79, and we found all the 31 automatically. The fully manual system did, but we also found an additional 12, which happened to have been published in a couple of weeks between their searches being done and the screening being completed. So there was one is it was a quite nice result in terms of like having better precision, less wasted time on the screening. But there's also something nice about the instantaneousness of this, that you sort of lose quite a lot of latency if people are able to screen things as they are produced, rather than having to go through a process of doing a search first. And so we've done one pilot review so far, and this is very, very early stage technology. It may or may not work more generally. We know it will only work in RCTs, and I think we probably have a lot of work to do in refining systems. I think we got very lucky with first review. It worked extremely well. It's possible other reviews will work less well, or some might work equally well. But in particular, if there's anyone present who is engaged, we're particularly interested in anyone who's doing the kind of process where they might do a systematic review, which involves some preliminary search or some first stage searches, and then a smaller update search done later on, nearer to the publication time. And what we'd like to do is to run some pilots of using Robot Reviewer in parallel to your existing review. So what would happen is, if you were willing, we would train a model based on your preliminary searches, and we'd register a review in Robot Reviewer Live system. And anyone who wants to participate would get pinged if there was any articles, and you could use the system and try it out. And the idea is that we would compare the retrieval of both systems and figure out, is this something which is working well, which kind of topics does it work well in, or is there any things that we need to improve upon in the design. If anyone is in that situation and would be interested in participating in the pilot, we're in the process of running it, or just starting running it right now. So I'd be incredibly pleased to hear from anyone, and please do reach out to me by however. My email is there, and I'd be really delighted to hear from you. Okay, that's my talk. Thank you very much, and I'm sorry I didn't stop for any questions along the way, but I'm happy to having now.
Thank you, Iain. That was awesome. So we do have 2 questions in the chat, but if somebody would like to raise their hand, we can also take those as well. So the first question that was asked actually anonymously was, it seems that there are almost as many publications as there are people in trials. There seems to be a lot of publications, many poorly done, and the results being not much actionable research. Does your work help mitigate that dynamic?
Well, I hope it contributes to mitigating it. I don't. I think maybe slightly. I think that's the aim of all of evidence synthesis, really, isn't it? And I think that it's one evidence synthesis tool that could be used to try and help. But I think, I mean, certainly, I think that there's a lot of these technologies have potentially got really solid uses outside of the conventional systematic review, because systematic reviews aren't done on every topic of interest. And if you're someone working clinically and you want to go and find out the results of some studies and no one's done a systematic review, you can't read trials, you can't read in a 10-minute consultation with a patient or something. So I think these sort of technologies to try and surface the best research quickly, I think, yeah, it does have some potential.
Okay, great. So our next question is regarding PubMed Medline and automated tools such as TrailStreamer. Have you noticed or do you anticipate a change in the accuracy of results, good or bad, as NLM moves to automating indexing? I'm thinking of having a machine on both ends of the search, so to speak, and if there are many, if there may be pitfalls, advantages there as opposed to a human on one end and a machine on the other.
So it very much depends on what these models use. And so in particular, the models I presented today, they only rely on the mesh terms to a very limited extent. And in fact, the only one of the pico terms that all the other data extractions don't depend on anything from NLM, which just uses the plain text from the title and abstract. The only exception is the trial, so the study design classification, where we use some information where it exists, but we have a backup system of using just the text alone where it doesn't exist. But so you do have it's very slight, but there's a very slight worsening of accuracy in the study design classification where you don't have any mesh information on that, but it's not a dramatic difference.
Okay, great. So another question by Evan Sterling says that chart you showed halfway through was very interesting about RCTs per year detected by PubMed filter versus your method. Do you have any ideas why PubMed has missed so many trials in the last 5 years?
Yeah, and so they probably haven't missed them. They just probably haven't tagged them yet at the time of the assessment. And NLM's moved quite largely to some automation, but because there's a manual step, I think it's just a backlog. I think their official, I can't remember exactly what it is, but we spoke with them, and I think the delay was supposed to be somewhere in the region of 6 to 9 months it could take for a median time for an article to be classified, and I think so largely the sort of in quotes missed RCTs, essentially the recent ones. And I think the difference is that when you do it automatically, you can say which RCTs are published today. We have that result within minutes of a new batch on LM. So I think that's the difference. And I'm sure if you went back and checked it, now you'd find that some of those older ones have been found, and probably would be another section of the current ones not quite tagged yet.
So the next question is from Celine, who asks, do you envision adding additional databases besides PubMed and ICTRP in the future?
Yes, one of the challenges we have is many of the databases that people use are proprietary, and they cost a lot of money, which we don't have to access, and so that's a big thing. So I mean, that's a prohibitor for us using things like Embase, but PsycInfo, and there's a number of others which are just essentially unavailable to us unless we, I don't know, spend tens of thousands of pounds. But the one in particular which I'm working on is a really interesting database called OpenAlex, which is a non-profit who have taken over Microsoft Academic Search, and they have a really nice database of currently about 300 million articles, and some preliminary work suggests that it has really, really good coverage for systematic reviews of interventions, and probably quite a lot wider. So that's our next goal.
Oh, great. I actually also know of another, an AI website called illicit.org, and they're actually, I know that they're tagging systematic reviews. I'm not sure if they're tagging trials or not, but it's, I think,
Yeah,
illicit.org. It's a nonprofit from the US.
yeah, it's I had a look at that. It's very similar
Oh, is it?
methods to what we're doing, I think.
Oh, great. Okay, so one question by Michael, have you done any work with observational studies? And if so, what are the prospects for applying some of the approaches to subsets of observational studies, for example, prospective cohort studies?
Yeah, so one of the problems we've had traditionally is we've needed large amounts of labeled data to go and do this work. And so oftentimes we're either finding existing bodies of research, like say the Cochrane reviews or something like that, which tend to focus exclusively on trials, at least in volume, and otherwise getting people to label stuff, whether it's crowd labeling and so on. And these data sets on the whole don't exist en masse for other study designs, which has been a bit of a barrier. However, we're recently doing some work, and we have been working on being able to classify accurately these other study designs. We have a range of study designs, observational cohorts, case controls, systematic reviews, and guidelines, and a few others, qualitative studies. And so what we would like to do next is have a sort of a bigger version of TrialStreamer where we have all these types of study designs in there as well. And what we probably will explore is how well some of the models trained on RCTs will apply across. And I think in some cases they work quite well. So I think the PICO are preliminary impressions are that PICO seems to transfer quite well, but we haven't evaluated it properly yet.
Oh, great. And so just a follow-up question to that, like how big of a data set would you need, right? Like that is already pre-tagged so that the machine can learn off of that. Is that what you're doing?
Well, for these study designs, we're using some of the tags from PubMed to go and train on.
Oh, I see.
And so the general process is there are kind of small sets of data which different information specialists have been working on in terms of developing their manual tags. And so I think the rough plan is that we'll try and train on large volumes of the PubMed mesh labeled articles, and then try and find smaller sets of the kind of gold standard labels from these other studies and see if we can evaluate on those types of data.
Interesting. Yeah, great. Um, and actually, I have a question too. So I was thinking about the future of AI, right? Like, which you haven't really talked about because you've done a lot of work on here. You probably have some insights about that. But where do you see this going in the future? How long will it take us to have like, maybe a full-on, RCT classifier for all biases, or, where do you see this going in the future?
I think, well, I don't know. I think that there's a chance that it's almost an impossible task. I think that anything which will intrinsically require some human subjective judgment in it will mean that it'll have to be some co-task with machines and humans in there. And I think risk of bias, for example, will definitely be there. I could see models getting a bit better, and I could see that, especially when, like for example, the new version of risk of bias tool aiming to improve the inter-annotator agreement, because that's really poor with the version 1. People disagree a lot, but it might not necessarily be because the tool is bad. It might be because we have an inherently subjective task and experts don't always agree. I think that's ultimately the challenge. And I think these sort of, if you separate all these review tasks into sort of the laborious drudgery and the human analytics stuff, I think that anything which requires human analysis really is going to be another generation of AI. So it's not anytime soon.
Yeah. And is there any sort of talk about asking, even researchers and academics, anybody else doing research, to use standardized language so it would be easier, using these tags that are already like, used, say, for example, in PubMed, asking,
Yeah.
actual
Well,
researchers to
there's
use these tags?
Yeah, and I mean, there's as my collaborator Baron will often say that we're doing research in an area which shouldn't exist, because you know, there have been these defined structured formats that people should be or could be reporting trial results in, which have existed. You know, I think like IDASIM developed some of these ontologies like and literally now decades ago, but it is. People don't use them, and people do write in non-standardized language. And I think there's probably a couple of reasons for that. One is some sort of inertia for adopting best practice, but also I think a lot of it is that a lot of doing research is quite murky. I think that a lot of clinical trials, you know, things which are unexpected happen, or people have the wrong, you know, the example of COVID vaccination research, people have the wrong dose of something. And so trying to, even if one was able to collect all that in a standardized structured format, which was useful, even the analysis, it would still involve someone sitting there with a pile of structured data, think, what on earth do I do with this particular label? So I think yes and no. I'm skeptical about whether better description would help. Apart from the better you know, all the sort of stuff from Consort about describing your methods well, which should be done. That's certainly a good idea.
Yeah, definitely, I agree. So I guess we're over time, but thank you so much. It was so informative. I love learning more about AI and how it could be used in our work, even like to help us with, you know, whatever 5% of what we're doing. You know, I think it's going to be super useful in the future.
Thank you, and thanks for the invite to give the talk.
Yeah, and thank you everybody for joining us.